Hey everyone, we are going to cover isentropic flow first of all, okay? And by the way, you can look over here and see my dog. That's my dog Minnie, by the way, okay? So she'll be moving around, I'm sure, in these videos. All right, so first we want to define what isentropic flow is, because that's going to be important when we deal with compressible flow, which is what we're talking about, okay? So when we have an isentropic process, that is basically a process that is going to be adiabatic, right, keyword there, and reversible. Another keyword right there. All right, so let's think about what those two terms mean. So let's start with adiabatic. So when we say we have an adiabatic process, what does that mean? Do y'all remember back from thermodynamics? So when we say we have an adiabatic process, that means we got a process in which no heat is added or taken away. Okay, so that's what we mean by adiabatic. Okay, so if you look at that delta Q term, that's going to be 0. And remember, we talked about delta Q in the last lecture. We had the specific heats and all of that stuff. So that term would go to 0. Now, this does not mean that you won't have a temperature change. You could still have a temperature change, but you're not adding heat or taking heat away. All right, because there's other ways of changing your temperature, right? You could change pressure, you could do, different things. So adiabatic doesn't mean no temperature change. Now the next one is reversible. So reversible, when we talk about that, that's going to be a process in which no friction effects occur. All right, so in this class, that's what we're going to refer to when we say it's reversible. No friction. So if we have these two conditions, we're going to have isentropic flow. All right, so now let's go over that in a little more detail. Okay, so for the isentropic flows, we already know that no heat is exchanged. Okay, so we've got that. And there are no effects due to friction. All right, so we just restated what we had already stated up here. All right, but it's important to realize those distinctions. So now let's draw one of our airfoils. All right, so there's an airfoil. And now we're going to have flow going over this airfoil, right? Because we've got air that's flowing across that surface. So if we look, let's draw some streamlines there. We're going to have a fluid element right here. All right, so here's our fluid element right there. Now what we're going to say here is that the shear stress that's exerted on the fluid element can be neglected. And why is that? So if you look at what we wrote up here, why would we say this? Well, we said if we have isentropic flow, we've got a reversible process, right? Shear stress you can think of as being like friction. So if we have a reversible process, that means we're ignoring friction, so therefore we're going to neglect the shear stress. All right, so they're all related. So let's just put reversible, so we can ignore that shear stress. And then again, we're not going to have any heat that's added or taken away from the fluid element. So that delta Q is going to be, it says element there, delta Q is going to be 0. Okay. Now again, let's make a note here. Remember what I said, just because the process is adiabatic doesn't mean the temperature is constant. Okay, so let's write, although the flow is adiabatic, the temperature doesn't have to be constant. Okay, so just make sure you understand that distinction. And let's write a reason why that might be. Okay, so let's put this is because the volume of the fluid element is going to change as it moves through the different densities. Whoops. It's not how we spell different. All right, so here's different. So we got different densities along the streamline. Okay, because remember, this is compressible flow, not incompressible flow. So our densities can change, right? Okay, so we've got this fluid element. It's moving through different densities along that streamline. Well, if we've got different densities, then we can say that the volume changes. Now, if the volume changes, if you go back and you think about like the first chapter you learned in thermodynamics, you related work to volume, right? Same thing is going to happen here. So if we've got volume that's changing, that means work is done. Okay, so now we've got work done. Well, if we've got work done, what does that tell us about internal energy? Well, that means internal energy is going to change. All right, so that changes. Well, and if that changes, what else changes? The temperature. So we can put the temperature changes. Okay, so all of these things all go together. And then, even though we have an adiabatic process, as you can see through all this, we can still have temperature change. All right, let's go to the next page. Okay. All right, so for incompressible flow, remember in that case we said our speed was going to be less than 100 meters per second, and rho was a constant. So that means volume doesn't change in that case. Which, if volume doesn't change, what does it tell us about work? There's no work done, right? Well, and if there's no work done, your internal energies are not going to produce that temperature change. So we're not going to have a temperature change. Okay? So that's kind of the difference between compressible flow and incompressible flow. All right. So that means our discussion of isentropic flow is only good for compressible flows. All right, so the equations that we're going to derive in just a second, you wouldn't want to use these equations for incompressible flow. We've already derived those equations previously, and you'd want to use those old equations if you've got incompressible flow. These new ones that we're going to derive are only going to be for compressible flows, and in this class, that means high-speed flows. All right, at least where we have speed greater than the 100 meters per second. Okay, so now let's go ahead and we're going to get our equations. And again, these are going to be for isentropic flow. So we already said it's going to be adiabatic and reversible. So we know we have that. Now if it's adiabatic, what's dq going to be? Remember, Q is heat. So if it's adiabatic, there's no heat added or removed. So this should be 0, right? So that's going to be 0. And then if we look at our equation that we talked about before, we've got our delta Q was equal to dE. Remember, this E here is internal energy, plus the pressure times dV, where this V is volume. So that's got to equal 0. Okay, because we already established there's no change in the heat, right? So that's got to be 0, which means this is 0. So with that, let's move dE over by itself. That's going to give us negative pressure times change in volume equals dE. Okay, now we already have an equation for dE, if y'all remember. We did that last time. Okay, so let's look at that. So from dE, we've got CV dt, right? That's what we derived before. So now that we've got this, well, we're going to make this substitution. I'm going to plug this in for dE. All right, so just take this, plug this in, and that's going to give us negative pressure dV equals CV dt. And remember, this CV, that's that specific heat of constant volume. Okay, so now we got this, and likewise, there was another equation where we had specific heat of constant pressure. If you do the same thing, you'll get the volume times dP equals Cp dt. All right, so those are the two equations you get from the specific heat equations that we looked at. Okay. Okay, so now that we've got these two equations right here, we're going to put it all together. Now what we're going to do is we're going to get a ratio. We're going to take this equation, divide by this equation. So let's see what that gives us. So we're going to have negative pressure dV, and then it's going to equal to CV dt. So just recopy that equation. And then I want a ratio. So on the left side, I'm going to divide this by V dP. And then over here, we're going to have Cp dt. Okay, so you're dividing this equation by this equation. All right, so now we've got that. Now, let's see. We've got some stuff that cancels out here, right? So that and that cancel, so get rid of that. Now, if you notice on this left side, let's look and see what we have. I have pressure here and dP here. Then I've got dV and V here. So I want to get these terms on separate sides so I can integrate. So let's do that next. So let's create an equation where we've got dP over P on the left, and then we're going to move everything else over. So that's going to give me negative Cp over Cv times d volume over volume. Okay. All right, so now we've got this equation. Now, if y'all remember from thermodynamics, this ratio has a symbol associated with it, right? So it's either K or gamma, depending on which textbook you're usually using for thermodynamics. All right, so I'm going to use gamma because that's typically what they use for aerospace applications. So we're going to say this is gamma. Now, obviously, this would change based on your substance. For this course, this is aerodynamics, right? So we have air. So we're going to have just one value to worry about, and we're going to say it's 1.4. All right, so that's for air. So if you had a different substance, obviously you'd need to recalculate gamma because you need to find these different values. But for this class, 1.4 is our value. And notice that that is a constant. right? Okay, so let's take this and let's replace this with gamma. Okay, so we're going to have dp over p equals negative gamma dv over v. Now look at that nice equation. So that one's pretty easy to integrate, right? Should be. Hopefully everybody recognizes what that integral should be. So we're going to integrate both sides. Remember that's constant, so we can pull that out. And we're going to go from P1 to P2. So this is the pressure at point 1. This would be the pressure at point 2, because again, remember, we're going from point to point. So if we draw our favorite airfoil and put a streamline over it, we would have point 1 and then we'd have a point 2. Okay, so these equations are going to allow you to relate one point to another point. All right, so that's the left side, and then over here, I need volume at point 1, volume at point 2. Okay, and then you just have to do the integration, which is pretty straightforward. So anytime you do the integral of, you know, dp over p, that's going to be the natural log, right? And then when you plug in your limits, you're going to end up with the natural log of P2 over P1. Then that's going to equal negative gamma, because that was constant. And then now we have the integral of dv over v. Well, that's going to be the natural log of v, and then we're going to plug in these two limits, subtract. That gives us this fraction in here. So we're going to multiply that by the natural log of v2 over v1. Okay? So now we have that. And if you look at this equation, I have natural log on both sides. So we can get rid of that and rewrite this equation as P1 over P2 equals V2 over V1. And we're going to raise this up to the power of negative gamma. Okay. So now we've got that. All right, now a lot of the times we don't want to use volume in here, we want to use density. So we can relate density and volume using these equations. So we'll just say 1 over density for V1, and then same thing for point 2. All right, so now we've got that. So when you plug these two in here, then what we end up with is P2 over P1. And once you plug these in, since they're fractions, you're going to end up with row 1 on top and then row 2 on the bottom. In order to keep it consistent, we want 0.2 terms in the numerator on both sides. So we're going to switch the sign of that exponent. All right, so let's just work through it. All right, so here we got V2, so we'll put 1 over row 2, put that over 1 over row 1. That's negative gamma. Well, then when you flip this up top, then you've got that row 1 over row 2, negative gamma. But I want the 0.2 terms in the numerator on both sides. So now let's just switch things around a little bit. So now let's just do P2 over P1. That's going to equal row 2 over row 1 to the power of gamma. Okay? And this is the function that you'll normally see that relates the pressure to your density terms. Okay, so definitely pay attention to this one. This one's only for isentropic flow. All right, so make sure you make a note of that. And then if you go in, notice we've got pressure and density here. If you go in and you use the fact that this is rho, that rho equals pressure over RT, then once you plug this in here, you can get a relationship between your pressure and the temperatures and things like that. Okay, so what we'll get with that is we'll get P2 over P1 equals T2 over T1. And when you do the math, you end up getting an exponent of gamma over gamma minus 1. All right, so now we've got that relationship. Now notice this temperature ratio is still equal to this pressure ratio. Well, this pressure ratio is equal to this density, right? Ratio. So basically you can set them all equal to each other. So then you can say that this temperature term equals rho 2 over rho 1 to the power of gamma. All right, so those are going to be your main equations right there. And again, this is for compressible flow only. All right. Okay, so let's stop here. This video is already 21 minutes. So we'll stop it here. We'll pick it up in the next one with an example. All right, see you then.